Hi, I'm Metta Spencer, and I'm going to have fun today. Listen, I've already started a conversation about fertilizer, and that's absolutely the best way to start a day. Wouldn't you agree? I've had, we've only been in touch about 2 minutes, and we already got deep into things like bonds between nitrogen molecules. We're off and running. My guest today is Ralph Martin, who's a professor at University of Guelph in agriculture. That's what they do best there. They do a lot of agricultural research. And he tells me that he knows a lot about organic farming. And that and the good thing about organic farming is they don't use a lot of artificial fertilizer. So listen, if you don't think that you're interested in this, just wait. Hang on, give me about 5 minutes and it's going to really curl your hair. All right. Good morning, Ralph. How are you?
Doing well, thanks. Good to see you.
Good. Okay. Well, thank you for doing this. Where do we start? I tell you where I start. I don't know a damn thing about fertilizer. I did last week. And I read up a little bit on Wikipedia and things in the meantime, and I've already forgotten it. But listen, it turns out that we got a problem because, tell me if I'm wrong, I think it was Wikipedia that told me this stuff, that about half of the food in the world that is produced and obviously consumed is here because of fertilizer. Without it, we wouldn't have it. On the other hand, the damn stuff is killing us. I mean, it's causing all kinds of environmental problems. And I've heard things, really awful things about what might happen in the long run. Like, I won't even go there. But anyway, the business of the runoff of fertilizer from land into the waterways and lakes and rivers and then to the ocean, that it causes all kinds of phytoplankton to grow and algae and things like that. So that's my highly scientific analysis of our problem. Tell me what a real scientist would say about it, Ralph.
Well, I think there is an issue with fertilizer. Now, when we look at our modern food system, and according to the way we structure it now, yes, about half or 50% of the food that we eat is there because of fertilizer. But we have to keep in mind that in our modern food system, a lot of the crops that are grown to feed livestock. And that's not the most efficient way to use our land. That is to grow crops to feed livestock and then we eat the livestock. Furthermore, in Canada, we waste anywhere from 40 to 52% of the food that is produced. So there's a lot of waste in the system because of how we feed so much to livestock. And also, we just literally throw a lot of food away. The most waste is at the household level. And then there's some in processing and distribution and a little bit on the farm as well. Now going back,
let me, because you've given me an opening to talk about one of my pet grievances. I have friends who will come to my house, go to my refrigerator, start inspecting the expiry dates on all these jars and cans, and without sniffing at them or tasting them or even looking at it, they throw it away out of my fridge. Because they think that an expiry date is something written by God and carved like on tablets of stone or something, and you really have to obey it. And I believe that a hell of a lot of those things are just made up without any basis whatever. And that how do they know when my food is going to go bad? I think what people should do is look at it, smell it, maybe taste it, and then if something looks wrong, throw it out. But I don't believe in expiry dates. Now, you can argue with me.
Yeah, no, I tend to agree. I think most of them, we usually call them best before dates. And that's really what they mean. The food is best before a certain date, but it certainly doesn't mean that it has to be thrown out after that date. And our research at the University of Guelph, I worked with a team, and we went to homes and collected their compostable waste, and we went through it and sorted it all out, and we had all the data, and then we went back and did surveys in the homes, so we knew exactly how much they were wasting in each home. And in the survey, we started asking them questions, and one of the things that really stood out to me was that the more awareness they had about food, the less they would waste. And those who had several criteria for saying that food should be thrown out tended to waste more. Those who just had one criteria, and the one that really stood out was a smell test. Those who would smell it and decide on that basis whether or not to throw it out wasted much less. And as far as we know, they were all healthy.
Yeah. The only time I've ever gotten sick from food, eating bad food, was when I actually think I ignored my own evidence and, went ahead and ate it when I should have known better. So it wasn't, and nothing has ever made me sick otherwise. Anyway, so there we go. We have a new campaign to work on, is to tell people to at least smell the stuff before you throw it out.
Absolutely.
Mm-hmm.
Yeah.
Good. Yeah. All right. Now, go on. I interrupted you because that happens to be
I just want to go back to the food system. Yes, yeah. If we continue with our current food system, the way it's structured, then yes, 50% of our food that is produced depends on fertilizer, particularly nitrogen fertilizer. And I'd like to just make a distinction between the fertilizers. There's nitrogen, there's also phosphorus. I'll come back to nitrogen, but phosphorus needs to be mined. And the greatest reserves now are in China and Morocco. Florida did have big reserves of phosphorus. They still have some, but that's being used up fairly quickly. And then the other one is potassium. And in Saskatchewan in Canada, we're well blessed with lots of potassium. So we have that. So those are the big three, the ones we call the macronutrients. There are many, many micronutrients. And depending on the soil and the region where you are, there might be a deficiency of selenium, for example. I worked in Nova Scotia a long time, and there tends to be a selenium deficiency there. So it's important there to make sure that you're not being limited by selenium, for example.
What happens if you're short of selenium? What does the body do?
It affects the health of livestock, and it can affect human health as well, and the plants. So it's important to not be deficient. But coming back to nitrogen, which is the main nutrient that we think about in agriculture, the important thing to know is that the Romans knew from way back that legumes are very important. Legumes are plants that fix their own nitrogen. I can explain that in a minute, but they can take nitrogen from the air and change it to a form that can be used by the plant. And legumes are all the beans and peas and so on, soybean, garden peas, all those. Some of the forages like alfalfa, clover, those are all legumes, and they can do that. What they do is that they cut a bargain with bacteria. Mm-hmm. And in the case of soybean, for example, the bacteria that they cut a deal with is rhizobia. So the rhizobia says, legume, soybean, I would like some of your carbohydrates. You're doing photosynthesis. I can't photosynthesize myself. I need some of your carbohydrates. In exchange, I have the key that can break apart the nitrogen molecule. So nitrogen molecules in the atmosphere are N2, and they're held together by 3 bonds and very difficult to break apart. But the bacteria, in this case rhizobia, has the key to break apart that bond. And then once a nitrogen molecule is separate, it's got these 3 bonds, and it can pick up hydrogen from the atmosphere for NH3, which is ammonia, and then one more, which is ammonium, yum, yum, yum. That's what plants eat. And it's ammonium, which can also convert to nitrate, which is a form that plants prefer. But the initial thing that bacteria, or in this case, rhizobia, can do is they have the key to break apart those bonds so that legumes then have nitrogen, or the rhizobia is broken apart. There's the nitrogen. It's available to the legume. Now, the legumes are mostly selfish. The soybeans and the beans are particularly selfish. Most of their nitrogen goes into their own seed. Crops like alfalfa and clover are not quite as selfish, and they will allow more of that nitrogen to go into the soil through the root system. The soybean will allow some to go into the soil. And then if you have forages that, like alfalfa, clover, that have fixed their own nitrogen, it's gone into their shoots. And then in the next year, you grow another.
Hold on. You used a word, fix, nitrogen fix. A fixed nitrogen is, I didn't know what that meant. You say it means going into their own shoots? Or
No, fixed is the process of breaking the bond and attaching the hydrogens. Okay. That's fixing it into a form that plants can use. That's where the fixation is.
Okay.
They've broken apart like N2 is a gaseous molecule. So they break that apart and fix it in such a way that it becomes available to plants.
Now, you mentioned that legumes do, and I've heard that all my life, but I believe I've also heard more recently that certain trees can fix nitrogen too.
Yeah, there are some leguminous.
That wouldn't be a legume, but how do you know, how many plants are there that will be able to do that?
Many. There are many leguminous trees that can fix their own nitrogen.
So that's what the word legume means, that any plant that can do that is a legume.
There are other parts of that definition, but that's the one that's of interest to us now. Yeah.
Okay, thank you. All right.
Yeah.
All right. Now, apparently it's the nitrogen that is really crucial, or you say there's phosphorus and potassium.
Correct. And you don't want any one of them to be limiting. If you want to grow a crop for maximum yield, you have to make sure that none of the macronutrients are limiting. In fact, you don't want the micronutrients to be limiting either.
So you have to have all three and plus micronutrients in order to get the maximum, or maybe any benefit from this from these legumes doing their magic stunts.
Well, you don't want to have anything limiting to any degree. Sometimes the limitation will have a quantity effect, as in yield, like how much seed there is that the plant produces. Sometimes it will have a quality effect. But for the macronutrients, for the most part, it's both. And you want to make sure that none of them are limiting. If they're limiting, then you'll have a lower yield.
Okay, well, now that already answers one of the questions I wanted to ask you in the long run. But let me back up and tell you why I got interested in this. Mm-hmm. Because I read something, and well, I often do talk shows with a guy named Michael Barnard out in BC, who follows all kinds of new technological innovations. And he did something about an outfit that is in California, and they were trying to figure out ways of reducing the amount of fertilizer, or at least artificial fertilizer, that needs to be applied to plants because of the harmful side effects. And we haven't really talked about all those negative side effects that the that the fertilizers give. But and they were thinking of ways of trying to find something that would help break apart those nitrogen things. But then they decided, well, what if we just found a way to make it difficult or impossible for the bacteria to sense the presence or absence of nitrogen. They said normally what happens is in the soil, the soil contains bacteria that do this, breaking the nitrogen things apart and making it available. But to do it, they have to sense whether there's plenty of nitrogen around. And if there's a shortage of nitrogen, the bacteria will do their job. But if there's plenty, an abundance already, or what they consider plenty, they don't do it. So they have a sensor that enables them to say how much nitrogen is available there. And they only do their job if it seems to be needed. Well, suppose you turned off this sensor so they can't tell whether they need to. They will go ahead and do this nitrogen fixing. Anyway, I may be distorting things, but I'm sort of warm anyway in my description, I think. They will go ahead and just keep making nitrogen, if you will, indefinitely, and keep supplying more and more and more of it because they can't find out that they've already got enough in the soil and they could stop. So what they've done is they've created bacteria that have these sensors turned off, which means now what they are doing, this company will do things like coat the seeds before they plant them, coat it with this chemical or whatever it is that does this, so the bacteria can't turn off their production of nitrogen. And then later they may go back and put some more in the soil around the seeds. But this chemical, this changed or altered bacteria then go on and keep making nitrogen so that they don't need to use so much fertilizer. Now, they say that right now they can reduce the need for fertilizer by 50%, and they're looking to be able to reduce it by 100%. I want to interview these people sometime and find out, but I need to know more before I do. And some of the other things that occurred to me was, well, that just handles the nitrogen in the fertilizer. Let's assume that it does everything they hope for. They claim that they can really reduce the use of fertilizer enormously globally if people will adopt this technology. But if you still need phosphorus and potassium and these micronutrients, what do they do that's so essential? And why does anybody think they could get along without them? Because those are part of fertilizers, right? Every fertilizer contains some mixture of at least those ingredients. See my question?
Yeah, there are a number of parts there, like getting access to all available nutrients, including phosphorus, potassium, and micronutrients, is partly a function of soil health and microbes that are in the soil and giving the plant access to those nutrients. And in the modern industrial agricultural system, I'll call it, we've relied less on that and more on making sure all those nutrients are in the soil. Now, with respect to nitrogen and the plants that can shut off the sensor that indicates that there's nitrogen in the soil, I think that could be really risky because you don't necessarily want a legume that just keeps pumping out nitrogen into the soil. The losses of nitrogen are as nitrate. That's what plants like to take up. But if they don't take it up, or if the bacteria just keep producing this, there will be two problems. One is they're going to have to use carbohydrate from the plant. That's the deal, after all. The bacteria need carbohydrate from the plant to do what they do. And if they just keep pumping out the nitrogen, and if it's more than what the plant needs, and this sensing system doesn't work, you're just going to have more of it going into the soil. And that's not a good thing. So I'd want to be very careful about that technology. I go back to organic farming. In organic farming, in crops like soybean, our yields on average are about 5 to 10% less than non-organic farming. And with all legumes, we're like that. With corn, we might be 70% or 30% less than what non-organic farming can do with fertilizers. But with organic farming in the long run, once we have soil health set up and we have appropriate crop rotations, we can still get pretty good yields. And I want to go back to the system. Why would we want to produce so much food that we can waste anywhere from 40 to 50%? What's the sense in that? Is it not better to produce what we really want, or what we actually need is a better word than want, and to make sure that it's healthy, than to produce so much that we can waste 40 to 50%? And why is it that we're using so much of our prime agricultural land to grow crops to feed livestock? In my book, Food Security, I have a chapter on feed for livestock, food for people. I think livestock should only be consuming feed that is plant material that people cannot eat for whatever reason. For example, we cannot eat clover and alfalfa and get much value out of that, but a cow can. A cow can eat alfalfa and clover. She can convert it to milk, then we can drink the milk, and that becomes a fairly synergistic system. And then the cow has manure and so on that can go back into the soil. And forage legumes like clover and alfalfa are the best plants there are for soil health. And to maintain soil health in the long run, we need forage legumes and forage grasses as well. And we need those systems to maintain soil health. We could do it without ruminants, but many of those plants have evolved with natural systems with ruminants, and it seems to me that there is a role. I think if all the beef we ate or all the milk we drank was from cattle that only were grazing or only had grass or clover, we'd have to drink much less milk and eat less meat. And I say, so be it. That would probably be better for all of us.
Mm-hmm. Okay, well, I had a talk show with a man named Frank Mitloehner, who is a professor at UC Davis, University of California, Davis, and his entire research has to do with the burps of cattle and the gases that are produced by this enteric fermentation in the gut or the stomachs of the cattle. And so on. Of course, he is very enthusiastic about the cattle raising and about being able to do it better. I was extremely convinced by him that it's really a good thing. Now, he didn't talk about clover or other alfalfa. He just talked about grasses. And I've heard that the Midwest, where the bison used to live, the grasses had roots that were like up to 6 feet deep, that they were very long rooted, and therefore those grasses could sequester a whole lot more carbon than the short grasses that are grown there now. I haven't heard any discussion at all about clover or alfalfa, but his analysis was that and it makes sense to me, that the methane that's produced from a cow is, of course, it's the same methane technically, but it's different in the cycle from methane that's mined from underground that's been there thousands of years and stored away, because we're digging up this methane from, or the carbon from petroleum and whatever coal, and adding it to the carbon in the atmosphere. But when it comes to the animals producing methane from their burps, it's part of a closed cycle that's been there forever. They emit the methane, it goes into the air for about 10 years, it breaks down, it's absorbed as CO2 by grasses, which human beings can't eat, but only ruminants can, absorbed by the grasses. The ruminants eat them, they produce the methane, etc. So you keep the cycle going, but if you don't add numbers of cows to your herd, you're going to have the same amount of methane being produced that was there in the first place. So you're not adding anything. You're just putting it back into a closed cycle. So
I think for the most part, that is generally true. I think it depends what we feed ruminants. Ruminants are especially adapted to eat forages, that is grasses and clovers. Mm-hmm. And there's a study at the University of Michigan a few years ago that showed if you have livestock like cattle in a feedlot, the net emissions, CO2 equivalents, like taking methane, nitrous oxide, and so on, to CO2 equivalent, then you have about 6 kilograms of CO2 per kilogram of meat. But if you have those livestock grazing on pasture, including the sequestration of CO2 from the atmosphere by the grasses and the clovers, then you have a net sequestration of 6 kilograms of CO2 per kilogram of meat. So I think it's really important to think about what livestock are being fed. And when you look at grain, then you've got all the emissions associated with manufacturing nitrogen fertilizer. We've talked about the rhizobia that can break that triple bond. The way we have to do it as humans is really clunky. Ever since the time of Fritz Haber, shortly in about 1908, Fritz Haber in Germany figured out how to break apart that triple bond in the lab, but he had to do it with heat and pressure. So to manufacture nitrogen fertilizer requires a lot of energy to get the heat and the pressure. Now, since Fritz Haber's time, it was his buddy Bosch that figured out how to scale it up. And so we have the Haber-Bosch process to make manufactured or synthetic nitrogen fertilizer. They needed a lot of heat and pressure, therefore a lot of energy, and you need natural gas as a source of hydrogen. When you've got that spare nitrogen with all the free bonds, then you need hydrogen to put onto it. So you use natural gas, use lots of energy to get the heat and the pressure. Now those systems are a lot more efficient than they were at the time of Bosch and Haber, but they're still using quite a bit of energy. And so generally, when you look at a curve of nitrogen fertilizer use, it goes right along with energy use. So phosphorus, potassium are mined.
Wait a minute, I've lost you train of thought. When you have something going, it goes along with what?
Energy and nitrogen go together. It takes
the amount of energy that is used to produce nitrogen. The more nitrogen you want to produce, the more energy you have to use to do it. Is that it? Okay. All right.
So as nitrogen use goes up, so goes energy use. The most energy consumptive process in all of agriculture is the manufacture of nitrogen fertilizer.
Oh.
Way more than transporting food all around the world, way more than tractors working in the field. The most energy consuming part of agriculture is the manufacture of nitrogen fertilizer.
So that is one more reason why you don't want to use artificial fertilizer.
Well, not too much.
Not too much. Okay. But before we go with this, because that's obviously where we need to go with that conversation, but let me go back and say what Frank Mitloehner told me that disagrees with something you said. You said, I believe, that it takes less CO2 emissions to produce a pound of beef if it's fed by grass in a pasture than if it's fed in, let's say, corn in a feedlot.
That's correct.
Right. Okay. Now, what he said is the opposite. He said that all of the cattle are normally fed grass anyway, except for the last month or two, I don't know how long, the final phase of their life where they're put in a feedlot. And what happens there is they're fed corn or something else, and that fattens them up. And they not only the meat tastes better, apparently people prefer that kind of meat, but also more important, they grow faster. So the lifespan of the cow is shorter if you have the ones that are put through the feedlot finishing than those that spent their entire life just eating grass. In fact, they're so much longer that in this lifespan, the longer lifespan of the cattle, the grass-fed thing, they're going to produce more CO2 than the ones that are finished with the corn. And therefore, that the meat that's produced from corn-fed or finished beef is less CO2 producing than the ones that are fed on the grass.
Yes, I've heard the argument, and I think what he's saying, if I'm pretty sure, is that per animal, an animal in pasture might have produced more methane than an animal in a feedlot, because the animal in the feedlot has a shorter lifespan. But if you talk about per kilogram of beef, and if you talk about animals that are well suited for pasture, right now the system, the packers want large framed animals so that it's more efficient for them to do the packing. And those animals have become much more popular with feedlots and feeding grain, and they can make them larger framed and more meat per animal and so on. But if you have an animal like a Angus or Hereford, the traditional British breeds that were on pasture, they will finish within a reasonable amount of time. You can finish them entirely on grass. I've done this research and I know it's possible. There's a fear that livestock that are the cattle finished on grass are going to have more yellow fat. We ran them through a slaughterhouse. That was not the case. It was a myth, but it's not the case in the slaughterhouse, or not, at least not to the point where they were downgraded for it. And it seems to me that what we want to keep in mind is that the grain, all the attendant CO2 emissions with grain from fertilizer, as I said, from manufacturing all the fertilizer, from the work in the field, the combining, the drying of the grain, transporting it to the farm. If you just have cattle on a pasture, all the manure is deposited right there. They eat their feed right there. Mm-hmm. And then the grasses are also sequestering CO2. So per kilogram of beef, I still would argue, and I stick with my paper that the folks in Michigan produced. I wouldn't dispute that perhaps per animal in a feedlot, he may be right, but you have to think about the size of the animal. There are a lot of things to take into account.
Okay, well, it's good to know. I mean, it's interesting, important, obviously, and a
lot more of that in my book, like in the chapter on nitrogen fertilizer, and I also have a chapter on feed for livestock and food for people, and I try to get into those issues there.
Well, one of the things that I think is there's a word for it, which I don't remember, but it is a kind of accounting that when they're measuring the amount of CO2 being or carbon being emitted per kilogram of any kind of food, they have to. This system takes into account all kinds of other things, such as the in this case, I'm imagining that it would include the amount of electricity that was required to produce the corn, the fertilizer for the corn that goes into feeding the cow. And so the meat production would for the amount when they try to estimate the amount of carbon emissions per kilogram of meat or compared with legumes or peas or whatever, they would count all of these factors like the electricity to produce the fertilizer to produce the corn, etc.
I think you're referring to a life cycle assessment.
That's it. That's right.
To have a complete life cycle assessment. Yeah, and I work with a few colleagues who've done that. And yeah, it's very important to think about water use, about the impact of pollution on the environment as you're doing this. There are quite a few factors they take into account when doing a complete life cycle assessment. Yeah.
Mm-hmm.
Just one more thing. Often people will say that cattle that are fed grain are more efficient and they don't burp and fart quite as much as cattle that are eating only grasses and clovers. So we tested that, and my colleague Al Ferdine and student Shelley Yerlink and Mike Main, we put cows in a chamber and we fed them a regular TMR, total mixed ration with a lot of grain. And we measured all the methane coming out. And then we also fed a cow in the same, we had another chamber next door, and we repeated this a number of times to get statistical significance. We fed her only pasture grasses. So the students had to go to the field, cut the grass and feed it to the cow. But she was getting only grass as she would get in the pasture. And there was no difference in their methane emissions, none at all. So I think the old myth that cattle who eat too many forages are going to burp and fart and emit more methane is based on old data where they looked at hay with fairly mature forage that wasn't in its prime as it would be in pasture. And in fact, in our experiment, what we didn't account for was that the students are not as good at selecting leaves as the cows are. When the cows go out, they'll go for the leaves first, which is where the nutrients are and there's less fiber. The students
like clovers grass, you don't call grass leaves, do you?
Well, grass plants have leaves, yes.
Oh, okay. So what the cows go for what as opposed to what when they're choosing?
They'll go for the leaves before they go for the stems of any plant.
Okay.
The leaves have the nutrients and the stems have more fiber, and the fiber helps to cause the enteric emissions.
Oh, okay. Okay. Well, now what you've said so far, at any rate, what I was waiting to hear you say people should stop eating meat, but that's not what you said. You said that we still need ruminant animals, but that we should leave them out in the pasture, right?
Yeah, and the paper from Michigan does a good job of showing that if we only ate meat from animals that are in pasture, we could only eat about 50% or perhaps less, because there wouldn't be enough land to produce all the meat we eat today. But I dare say that most people in North America eat at least 2 times as much meat as they should anyway.
I see. Okay. Okay. Now, I mentioned to him something that I didn't plan to bring it up about this meat eating issue, but it's something that has interested me a long time. I got interested in this Alan Savory holistic management notion. Yeah. And because that should be part of our calculations. If we're thinking about saving the planet, it's not only that we want to stop the carbon emissions in the atmosphere, but we want to save the quality of the soil. And that desertification is going on around the world hugely, and a much more drying up and brittleness of the soil. And that it is really herds of animals handled in a very specific way that is the best and maybe the only real solution to that problem. What do you think about that point? That whole, it's a school of thought now, or a whole area of work.
Yeah, no, the paper from Michigan was using an Allen Savory type of grazing. They called it multi-paddock adaptive grazing, I think, and it follows on the ideas of Allen Savory and making sure that you're doing crop rotation and you're moving or pasture rotation, and you're moving cattle in to a new pasture every day. Mm-hmm. And then the grass where they've just been has plenty of time to recover and regrow, and there'll be a whole lot of cattle in a small paddock, and it simulates the way buffalo grazed when they were in large herds compacted together by prey. The modern day prey the modern day predators are the fences. Like, the fences don't allow them to get out and force them to stay in a small group. And then they're moved to the next paddock, and they're not allowed to go back in there until that has recovered. I think that system is very good. And it goes back to what I said earlier about grasses and clovers are the best plants we have for improving soil health.
Mm-hmm. Okay. Oh, well, I'm so glad that you're saying all this. I didn't expect you to talk about animals at all. I thought we were just going to talk about how to, the quality of fertilizer and how plants get their nutrients. So let's go back. If we haven't talked really about what are the reasons for feeling that that fertilizer that is manufactured is dangerous to the planet, and that we have to reduce, if not eliminate, the application of fertilizers. Because I'm not sure, I do know that part of it has to do with the runoff of these chemicals into the oceans and into lakes and so on, causing eutrophication, I think. And please talk about, I'm not clear about all of the harmful effects. And is it just the nitrogen that causes that, or do we have to worry about, if let's assume that we could in some safe way do what these people are claiming to do with their modified bacteria and enable them, which enables them to reduce the amount of nitrogen fertilizer applied to the soil, but they'd still need to apply phosphorus and potassium, I gather. And is that as much of a problem for the environment as the nitrogen? And is there plenty? Are there plenty of supplies of potassium and phosphorus in the world, so that if we need to keep using it, we can keep doing so? But maybe it's also harmful. I don't know. Can you talk about the side effects of those chemicals?
Well, Lake Erie is mainly a phosphorus problem. Like, there's a lot of pollution in Lake Erie, and a lot of that is excess phosphorus. Some of that could be from sewage systems of cities along the shores of Lake Erie. Some of that is from agriculture. And some of it is, there's a nitrogen problem there too, with excess nitrogen. And that's one of the reasons I don't like what you propose. These people are saying they would turn off the senses on the bacteria so they would just keep producing. It's a problem of producing too much, perhaps at the wrong time when plants don't need it. I do want to give the fertilizer industry credit for the 4R system. It's the applying fertilizer at the right place, at the right time, with the right type of fertilizer and the right amount. And so that's being sensitive to plant uptake, applying it when the plants are going to be taking up the fertilizer, applying as much as they will use and no more, applying the right type of fertilizer so that it's the type of fertilizer that that particular plant needs, and applying it in the right place, like next to the roots of the plant. So the 4R system that the fertilizer industry in Canada advocates is something that I'm certainly supportive of. If you're going to use fertilizer, if you're not an organic farmer, then I fully support the 4R system to limit pollution from either phosphorus or nitrogen going into the waterways and then eventually into Lake Erie and so on. What we haven't talked about yet is manure from cattle. So in feedlots and so on, this manure can accumulate to the point that it becomes a real pollution problem, and there are a lot of nutrients there. I remember a study being done at Atlantic Canada 30, 40 years ago, and they argued that there was enough manure in Atlantic Canada to meet all the nitrogen and phosphorus needs. It was just a matter of making sure that we got the manure from the barns and the feedlots to the fields where it was needed at the right time. And mind you, it's bulky and it's not particularly efficient to move it all. But I think we need to start thinking in the long term about various sources of nutrients. And the ultimate circular economy is if we use our own sewage, the sewage of humans, the feces and urine that we have. And there are all kinds of technologies that we could think about to do that, recognizing the big problem are the pharmaceuticals that we take. We don't necessarily want all those going back into the environment. And then, of course, there are pathogens associated with sewage. We've got to find a way to deal with those two problems. But I think rather than mining more phosphorus in Morocco, we should be thinking about the circular economy whereby our own urine and feces goes back into the system. And organic farming, for example, right now won't allow sewage, and it's because of pathogens and diseases and so on. And I think that as we go into the future, we're not going to be able to afford to not use human sewage. And I think we'll look at that as a source of nutrients rather than mining phosphorus or using energy to manufacture nitrogen fertilizer.
Okay, I've got two lines of questioning here, or a comment. Again, partly from Midloner. He says that there's a huge industry in California growing now where they take the manure from feedlots and from dairies, because dairy cattle are confined and they can easily, collect it. And it goes into a lagoon, and they now put a tarp over the lagoon and capture the emissions, the methane, I guess, that's being emitted from that, which then becomes a biofuel. And then they take the what's left, the solid waste, and that becomes a fertilizer and is again applied to the fields. So that is part of the whole thing. And what was the most?
Well, I think what you're getting at are anaerobic digesters or anaerobic digestion. And we have that in a number of farms in Ontario now too. And I think anaerobic digestion is a really good thing to consider, because you can take the methane that is emitted and use it as, so it's a renewable natural gas. That's the common term that we're using for it right now, is renewable natural gas. And you can use that from anaerobic digesters. So you get that renewable natural gas, and then you can generate electricity or whatever, and you even get CO2 coming off, which can go into greenhouses and enhance plant growth. And then you still have the digestate, like the solids that are left over that you can spread in the field as a nutrient source. in California, it's much easier to do anaerobic digestion because they don't have the cold winters that we do. Here, where we have cold winters, you have to do this with large enough masses of manure so that it doesn't freeze. And the infrastructure to set it up is expensive, but once you have it set up, it's very efficient.
He says you make your money back in 3 years in California.
California, maybe, but in Canada, it would take a lot longer because the setup costs are much higher here.
Okay, now talk about pathogens. I don't know anything about pathogens in the soil, but I do have had several shows with Laura Kahn, who's a researcher at Princeton, who's written about antibiotics in the soil. And she says that when people, our antibiotics, even fed to cattle, which they, of course, for a long time were feeding large amounts of antibiotics to cattle to fatten them up, that these antibiotics then in the manure go into the soil and continue to be active and disrupt the functioning of the healthy soil, so that there are serious effects of having antibiotics in your cattle on the quality of the soil.
I think pharmaceuticals, whether for cattle, chickens, any kind of livestock, or for people, are causing real problems in the environment. And we have to figure out how to use less of these. This is another reason why I really like organic farming. We don't use those synthetic pharmaceuticals. And I think that we have to find a way to use much less, except that we might produce at a higher cost because we might not be able to stuff as many chickens into one space, or we might not be able to have as many cattle in a feedlot. We might have to spread them out a little bit. But I think we should accept those costs for the sake of healthy food and healthy soil. And we've got a lot of slack to work with. We're wasting 40 to 50% of our food in North America, and we're using too much of our land to feed livestock with crops, or we're growing crops on land where we could grow crops for human consumption directly, to grow crops to feed cattle, and we're losing all that efficiency. So we've got lots of slack in the system. It's a change of mindset that's required, I think.
Okay, well, tell me, you referred several times to organic farming. That's a concept I've heard all my life, but I'm now hearing more references to things like regenerative agriculture, which has to do with things like planting, no turnover, what do you call it? No plowing, and cover crops, and a number of other new, I don't know whether they're new, but changes that would be required in the normal conventional agriculture. Tell me where the cutting edge is. What is the prospect of our being able to sequester enough carbon in the soil through any technologies that you're now promoting to really make a big difference in reducing global warming? I talk to people, the estimates that I get from people who are concerned about climate change vary all over the map in terms of how much they think that we can sequester carbon by agriculture, what difference it's going to make. Tell me what's your best guess.
Well, there's a paper by Muller et al. 2017. I talk about it in my book, Food Security. And they show that organic agriculture, the big criticism of organic agriculture is that we would have to use more land to grow the same amount of food. But then I go back to the fact that if we waste less food, and they talk about this too, wasting less food and only feeding feed to livestock, not food. Right now, we're feeding food grade grain to livestock. We should only be feeding feed to livestock. So then we can afford to have lower yields. We don't have to use some of the pesticides and so on. The other criticism of organic agriculture is that there's too much tillage. But now there are a number of organic farmers, even with organic vegetables. And I was just at a farm a month ago where he is developing a no-till organic vegetable system. And it has, most farmers in organic that are using no-till have a system where they grow rye in the fall, it overwinters, and then in the spring, they come in with a roller. It looks like a rolling pin, but it's a great big one with edges on it, and it crimps the rye into the soil. And then they have a no-till planter behind the tractor, which can no-till seed right into that bed. And that system is now being used by a lot of non-organic farmers as well, because they can really reduce their pesticide use by doing that. So regenerative agriculture, coming to that question, is mostly about maintaining soil health. And I would argue that what I like about organic agriculture is that organic agriculture can be regenerative. Organic agriculture has a set of standards. There's a whole certification process. We know what it is by definition, according to the standards. Regenerative agriculture is still somewhat loosely defined. I don't see them in opposition. I see the best organic farmers as being regenerative farmers. I also really appreciate that there are a lot of non-organic farmers that are using some of the systems of regenerative agriculture, like no-till and cover crops and crop rotations. So it seems to me that there are a bunch of intersecting circles here. I'm still an advocate for organic because there's a whole set of definitions that goes along with organic, the set of standards, and there's third-party verification.
Mm. How successful are we, are you, or whoever, in promoting these changes? How quickly can you expect that farmers all around the world will adapt by, adopting these newer practices?
I think there are a lot of farmers that are really interested in adopting these practices. There's a group in Ontario called the Innovative Farmers Association of Ontario. A lot of them are doing a different work with regenerative agriculture. There's the Ecological Farmers Association of Ontario. They are doing excellent work. I've been a member of that group for 30 or 40 years, and they have all kinds of innovative projects, and they have a system called the Farmer-Led Research, where they do on-farm research to answer the practical farmers the questions that the farmers have, and it's based on their curiosity. And there's a young agronomist, Dr. Sarah Hargreaves, who's working with them, and some of those research projects get published in referee journals. So there's lots of adaptation there. I was fortunate enough to be able to start the Organic Agriculture Centre of Canada. That's been going now for 20 years. It's based in Nova Scotia. There's lots of research being done in organic agriculture across Canada, and there's more adoption of organic agriculture every year. So
Wonderful.
It is great.
Wonderful. This has been fascinating. I'd love to, let's do it again sometime, because there are a lot more questions in my head. And the longer I talk to you, the more questions I have. So thanks so much, Ralph. It's been fun.
Well,
Bye.
thank you. It's been a wide-ranging discussion. Take care. Bye-bye.
Bye.